Okay, hi guys. So today we'll be doing some disjoint set union problem on leetcode. So first take a look at this problem. Remove max number of edges to keep graph fully traversable. Keep things short, then we are given a graph, right? There are n edges. There are n vertex, and then there are some edges. These edges are split into three types. Type 1 are the edges that can be traversed by Alice only. Type 2 are the edges that can be traversed by Bob only, and type 3 are the edges that can be traversed by both of them. So we want to remove some redundant edges, right? We want to, like, for example, this guy, right? If we removed this 1, 2, mean we remove this edge, and we remove this edge, then the graph can still be traversable by Alice, right? She can still take this path, right? And from here she can take this path to visit all 4 nodes. So we can remove these 2 red lines, right? And how about Bob? Bob still need to keep all of the edges, right? Let's ignore these red lines because it doesn't affect Bob at all, right? So we have these 3 edges, and in order to traverse through 4 nodes we need at least 3 edges, right? So we cannot remove this, so we just simply keep it as it is. Okay, so what is the intuition to solve this problem? Like, we can see that the type 1 edge doesn't affect Bob at all, and the type 2 edge doesn't affect Alice at all, right? So the first intuition is that we can create 2 graphs for Alice and for Bob separately, right? So let's take a look at this picture, make things a bit clearer. So here is the edge that combine type 1, type 2, and type 3, right? So for Alice, then she really don't care about this guy, right? She really don't care about this green guy. So here's the graph for Alice. So for example, if we try to use a union file here, right? We try to union these disjoint vertex together. Okay, so now we union this guy to this guy. Okay, so now 1 is the parent of 2, right? We union this guy and this guy. Now 3 has the parent of 1. So these 2 guys already share the same parent. So once we try to connect 2 to 3 again, we can see that it's a redundant edge, right? So we will remove this guy, and same for no. Yep. And for this guy, is it redundant? No, right? So we keep this guy. So now to the red edge, we try to connect 1 to 2 again. Now 1 to 2 share the same parent, so we can remove this edge. On the 3 can remove this edge, and 2 and 4 we can remove this edge. So logically here, then we will try to see if there's any blue edge that we can remove first, right? Because if a blue edge is redundant for Alice, and automatically then it will be redundant for Bob also, right? And then we will try to run through the specific type of edge of Alice and Bob to see if we can remove any further edge, right? We create 2 separate graph for Alice and Bob, we're trying to find the redundant type 3 first, and then after that we're trying to find the redundant of type 1 and type 2 separately and add them all together, and it will form the final result. Okay, so I hope that makes sense, right? So we need to define our phi function, and since we are having a separate graph or set, union set for Bob and Alice, we can just pass the parent array here, right? So if x is not parent x, then we will do a path compression by parent x, and then we return parent x. Union, same as a phi function. We need to keep two separate union set for Alice and Bob, so we might have to pass in these two variable here, right? So if so the parents of x will be parent x, parent b will be parent y. I'm sorry. So if rank pair px is larger than rank py, right? And we just simply say that our parent of py is px, and then we increment the rank of px by 1. Else I'm sorry, here we need to pass in this parameter also. And then now we will create two separate set for Bob and Alice, right? So if you take a look here, then this is the vertex is actually not 0 index. This is 1 index, right? So we need to be really careful about this. So we would say that parent 1, parent 2, sorry, be equal to 0 I for I in range length. And plus 1, right? And the same for this guy. Okay. I think this is good. Then now we're trying to like loop through this edge, right? Loop through this edge array, and then try to union them. And then now the first thing we need to take into consideration first is the type 3 edge, right? We need to union the A and B in type 3 edge first to see if there's any redundant type 3, and then we add it to a variable called redundant, right? Okay, so for type A, B in edges, right? If type is equal to 3, right? We will be adding redundant A, B parent of 1 and 1. Now, you might say that why you only add the redundant from the graph of Alice, right? So because type 3 is actually traversable by both of Alice and Bob, and so let's say if we have two redundant type 3 hash for Alice graph and two redundant hash for Bob graph, and if we add them together, then it could be 4, right? But like in reality, then we only have one graph. So these two edges are actually the same edges, right? So we cannot like just double them up. So we could be redundant plus union AB pair 1 rank 1, and we will be doing this separately. Pair 2 rank 2. And now for we have taken into consideration the type 3 edges that are redundant. We now need to take into consideration type 1 and type 2 that are redundant, right? So we need to make some modification to our union function. So let's say if px is equal to pi, right? So we know for a fact that this hash is redundant, so we need to write redundant. First, it could be set to false. So if px is equal to pi, then we just return 1, right? Okay, and we don't actually need to union them up, right? Because it's redundant. You see the point here. Okay, we don't actually need to do this if else function to union the x and y, right? So now we need to take into consideration of type 1 and type 2. So if type is equal to 1, redundant plus union A, B, pair 1, rank 1, and if type is equal to 2, redundant. Okay. So last but not least, let's not forget the case where the graph of Alice and Bob is disconnected. What do I mean by that? Let's take a look at this example, right? So if you take a look here, then you see that ignoring type 2, right? So we have Alice can only traverse from 1 to 2 and from 2 to 3. She doesn't have any way to connect to the node 4, right? So the graph is actually disconnected. So Alice cannot reach node 4, likewise Bob cannot reach node 1. Therefore it's impossible to make the graph fully traversable, so we just return 1, right? So how are we going to do that? Now we have the parent array of graph Alice and Bob's, right? So if it's not fully traversable, then the parent, there will be two connected components, 2 or more connected components, right? If they are fully traversable, then all of the nodes should have shared the same parent node, right? So we can just do this. So if len set phi x for phi x of parent 1, right? For x in range n is larger than 1, or len, we just copy paste it. So if any of the graph of Alice or Bob is disconnected, then we just return -1, right? Once we handle the hash case, we just return redundant. Okay. Rank px structure rank pi. Take a this is what the hell? Let's debug this, guys. No. See if it works. Maybe some bug relating to the index. Oh, here. Some. Oh yeah, okay. What the hell? I don't know. Oh, wait a minute. Why? The hell? It's really annoying. Oh my god. I'm sorry guys. I don't know. Seems all correct, right? Oh, fuck. A pair. I'm sorry. Okay. Okay, let's come to oh my god, I know. Come to the second problem. Here we need to similar string groups. We need to group string that are similar to each other into one group and then count the number of group. So what two string x and y are considered similar if they are identical, or we can make them equivalent by swapping at most two letters, right? For example, tars, rats, similar. If we swapping this guy and this guy, we get the same result, right? So if we swap this to this, t to here, we get rats. So together these form two connected group by similarity, right? So we can see that actually tars and ars are in the same group even though they are not similar. Why? Because each group is such that a word is in the group. Oh my god, please don't. Basically then tars and ars are not similar, but ars is actually similar to rats. So they form a connection, right? So they are still in a group. So that's basically it. I know they find the most difficult to understand explanation for each problem. Why? I don't know why. So like we can think of each of these string as a node, and then we can see if they have an edge connect to each other if they are similar, right? So we try to group them up. So for this guy, we check for all of the other guy, and starting with this guy, right? If this guy and this guy is equivalent, then we try to union them into a group, and then we do the same thing for this guy and for this guy, right? So we actually can do union phi here. So let me walk through it. We need to create a function phi, and union is a general template for union phi problem, right? So we need to also create a function called isValid. That function will compare two string and return true if they are valid, else then it will return false. So how are we going to determine if two string are valid? Okay, so first, okay, there are actually gonna be two ways that two string are identical, right? If they are the same as each other, so if we comparing tars with tars, then they are similar and they are identical, right? Second case, if they are not the same, we can actually count the number of words that are different from each other, right? So if we here T and R are different, 1, A similar, R, T different, 2, S similar. So if it's exactly 2, then it is equivalent, right? Because like that's very common logic, because this is anagram, right? They basically contain the same character. So if we can like swap position at 2 indices and then return the same word, that must mean that there are going to be 2 positions in the string that have different character, right? So we going to create our function called phi x if x not pair x is equal to phi pair x as return pair x. Yeah, union xi. We really don't care about rank here, right? So this is pair x equal to equal to phi x phi I. That's union. Sorry. For I in range length. The anagrams, so they will have the same length, right? So we will do variable called diff. So if S1 is actually the character as index I of the S1 is different from the character at index of S2, then we will increment the diff by 1. So if diff is actually larger than 2, then we just return false immediately, else if we run exhaust this loop and not returning false, and we just return true. Okay, now need to look through these guys for chain range strings. We're going to only group two different characters together, right? So we cannot group this guy with himself. It will be redundant. So this condition is needed, right? So we're gonna check if need to create a parent array here. Basically, it will run from it represent each word, right? 0, 1, 2, 3. So okay, if parent of I is already equal to parent of J, it's not parent of J, which means they are not in the same group, then now we're going to union them. I, J. Now what if they're in the same group? If they're in the same group, then we don't need to union them anymore, right? So last but not least, we just return then set phi x for x in range length strings. That's basically it. I'm sorry. Small mistake here. And is valid. Yeah, okay. So this actually really not efficient, because, and the only way that it can work, because the constraint is relatively small, we need to do a double for loop here, right? Right. We need to do double for loop and then check for every possibilities. Yep. Okay, so that's it for today. I thank you for watching and see you guys later. I'm sorry because today I'm a little bit rusty. I've been coding from 2 hours till 6 p.m. It's been a long day. Okay.